Great. Thanks for setting that up, Sean.
And as a backup, we're resuming recording, and I'm going to set Shar and is Tim here.
Yes.
Set both of you to co-host just in case, make co-host just in case something happens to my, why isn't Shar a co-host? Something happens and I get knocked out of the Zoom. All right, Shar, take it away. It's all yours.
Sounds great. Looks like we have Stephen Curran, our great speaker for the day here. So I'll pass it off to Tim to walk us through the working group status updates.
Yes, good morning, everybody. Just give me 1 second here to share my screen so we can kind of all walk through it together. So yeah, good morning. It is June 15th today, and on our call today, we'll be reviewing some working group status updates, and then we also have a presentation from Stephen Curran. So thank you for joining us today, Stephen. I appreciate it. Quick reminder, we are under the Hyperledger antitrust policy, so please just be aware of that. Few announcements. We have a few upcoming speakers. We have Nick Steele on the 29th, Stefan Mui on the 13th of July, and then Dmitry Zagadulin on the 27th. So if any of these speakers look interesting to you, please be sure to come on back in a couple weeks. And then we also have a Hyperledger in-depth with the red data technology. So that's on June 21st, and anyone can register at this link right here. So jumping right in, it looks like the Hyperledger Indie Contributors Working Group met on the 6th. Was anyone able to attend this call?
Yeah, I was. I can give a brief update, but I wondered if it also might be useful to see if we have any introductions that anybody wants to make on the call. I think we've got a fantastic group here and probably a lot of new faces to this call. So if people want to take the mic and introduce yourself and talk about your interest in decentralized identity, now would be a great time.
Hi, James Kemp. I'm the CTO at Wigren, which is a virtual power plant company, and I think we might use this for IoT device identification or potentially also users. Thanks.
Thanks for joining. That's great. Mai Novak, it looks like you have your hand up.
Yes, thank you. Good morning, everyone. My name is Michael Novak. I'm with the Open Voice Network and been a longtime fan and student for digital identity. I'm very excited. I come out of the IoT world, so I see this as being a key technology enabler for this. But also recently, you may have heard of generative AI in the news at least once or twice in the last 15 minutes. And again, verifiable credentials and digital identity are a perfect fit for conversational voice, as well as tagging inanimate objects. I'm really excited to check Stephen's math today, and I'll run through generative AI. Don't worry, Stephen. I'll make sure you're doing it correctly, okay?
Awesome.
We're glad you're here. Any other introductions that anybody would like to make?
Hey, good morning. Steve Michaelis Martin from Boeing Vancouver. We also are working on a project to integrate the verifiable credentials in part of our authorization, access and identity and access management authentication mechanism. Sort of a variety of applications to it that we're researching at the moment. So this is a fantastic application. I'm interested in how this moves forward. So thank you.
Absolutely. Thanks for joining, Steve. I'll drop the meeting page link in the chat here. Let's see. Oops. So I think I dropped the wrong link in the chat, but I will correct that right now. Let's see, so that anybody can put their name on the attendees list if they would like. So great, unless anybody else has any announcements or introductions that they would like to make, we could continue on with the working group updates.
It sounds like that's about it then. Shar, I think we left off at the indie contributors call. Would
Yeah,
you
absolutely.
give us a quick summary of that?
Yeah, so we talked about indie community contribution, so a discussion about how they're really successful indie networks, just fewer code contributors. And so perhaps this is because indie just works well and deployments are pretty specific, but at the same time we have a roadmap of things we would love to add to it and see implemented. So just a discussion about that I think was really useful. And then we also spent time on the call going over open issues in Indie Plenum. Stephen, I don't know if you have anything you wanted to add about that discussion or what we did on that call.
No, that sounds about right. Looking forward to more discussions on where Indie's going and how we can figure out how to expand contributions.
Yeah, absolutely.
Awesome. Well, sounds good. Thank you for sharing. Looks like the Aries working group met just yesterday. Was anyone able to attend the most recent Aries working group calls? Okay. Well, it looks like they were discussing some OWF resolution and did peer status and unqualified migration stuff. If you want more info, these links will take you right to their notes. The Aries bifold group met on the 6th. Was anyone able to attend the Aries bifold call? Okay, looks like they're working on an update and discussing some key issues. The Aries Cloud Agent Python users group met on the 13th. Was anyone able to attend this session?
Yeah, I was there. Talked about an update on the BCGov code with us that we at Indicio are working on to update Akapai to use the Hyperledger version of a non-creds. And so talking about the refactors, got the MVP of revocation completed, which was a big step. And the things we're looking at next are the automated registry setup, genericizing the revocation registry recovery, test updates, cleanup as well. And we also talked about the 0.72 final release and merging PRs in Akapai. Stephen, I don't know if you again have anything you'd want to add to that summary.
I can figure out how to unmute. 0.82 is ready. We've got some final things going into that. And then we went into Akapai plugins and updates and progress we're planning on making to that. And we added a new maintainer to the project, which is pretty cool. All of those are covered there. Welcome folks to join us at the next meeting in 2 weeks, 2 weeks from this one.
Sounds good. Thanks for sharing. I believe we've met, I'm not sure if this was the same day as our last meeting, but was anyone at the latest Aries framework JavaScript call? All right, well, it looks like they're kind of discussing what the future of Aries will look like and how to get started. For more details, you can click that link. versus got an end of life. Hyperledger Anon-Creds. Looks like they met on the 5th. Did anyone attend the Anon-Creds call?
We've had a couple of meetings, yeah. Basically, that we're moving forward on the spec. We now have a mentor, part of the program, in the mentorship program, working on the spec. So we're moving that forward, and also some super interesting discussions on the 2.0 plans, and some of the substitutions of new ZKP stuff, which we're going to be talking about soon on this call, into Anon-Creds 2. So those are the topics going on in that working group.
All right, awesome. Thanks, Stephen. Looks like TOIP hasn't been doing too much. Looks like the diff didcom spec working group met on the 5th. Was anyone able to attend the didcom spec working group? All right, looks like they're working on ion compatibility for didcom 2.1, and then they're working on some new marketing initiatives for didcom. This is May. All right, unless I am mistaken, I believe that is all of our working group updates. Does anyone have any general updates or groups that we've missed?
Hey, Tim, just a quick call out. The Aries Framework JavaScript recently released 0.4.0. The team who's worked on that, including Ariel, Berend, and Kareem, are going to give a demo/workshop on Wednesday, June 28th. The link is in the chat. It's not really going to be a hands-on workshop, but they want to really go in depth on all the changes and the new stuff that's in the new release. So that's coming up in a little less than 2 weeks.
All right, very cool. Thanks, Sean. Yeah, I'll give a brief pause to see if there are any other updates or announcements before we hand it off to Stephen. All right, Stephen, the floor is yours.
All right, welcome. Let me share my screen and I'll jump into the presentation. Let me close that. Got chat open off to the side, so if anyone has comments, let me know. Let me leave that there. Well, not quite there because I can't see. There we go. All right, can you see my screen?
Yes, it looks great.
Thank you. Okay, this is a presentation that I did at the Open Source Summit in North America, or a similar one. So I'm using that. I've tweaked the slides a bit to adjust into it, but we'll share them. Up in the top corner, if you want to, there's this bit.ly di-ZKPs. That's the link to the slides themselves. So if you want to grab those now or follow along, I should probably put that in chat, but maybe someone can. So online identity with verifiable credentials, and then we'll get into the meat of it, which is ZKP using high school math, just to explain what ZKP, zero knowledge proofs, are. So I'll jump in. That's the agenda. Brief, since this is the identity SIG, there's not a lot you need to know about online identities, and then focus mostly on the zero knowledge proof section and what they are. So credentials, paper credentials, are what we use in the world. That's what we've used for 2,500 plus years. Many of them are for identity. There's ones down here of things like professional attestations, professional credentials, like, you know, I'm an engineer, I'm an architect, I'm a doctor, or I'm a lawyer, those types of things. There's supply chain, there's IoT certifications that could be for, well, I guess those are definitely not paper. But there's lots of paper credentials in the world, and the paper credential model is one that, as I say, we've used. An issuer, some sort of authority, gives a credential to a holder. That holder puts it into their wallet or puts it into their filing cabinet or puts it somewhere. And sometime later, in a separate transaction, a verifier wants to see that piece of paper for some business purpose. And so the holder pulls it out of their wallet or out of their, takes it down to the office of the verifier and shows them the piece of paper. And the piece of paper, in theory, and I put quotes around, proves who issued the credential. So there's some sort of marker on the credential that shows who issued it, who holds the credential. There's some sort of binding on the credential between the person presenting it and the credential itself, and some sort of verification that the claims are unchanged. And proves is done because the big thing here is concerned with forgeries and things like that, that the holder somehow manipulated the document, either created it themselves or altered it in some way. Trust is largely this between the holder and the verifier, but there's also the trust between the verifier and the issuer. The verifier chooses what issuers, the credentials of what issuers they're willing to accept. So when I talked about that, there's both a technology and a governance aspect to it. Does the technology, does it look like it's on the right paper? Does it look like what that organization, that issuer organization produces? Does it look like there's ink marks on it where I changed my date of birth on my driver's license so that I could use it for other purposes? And then the governance is things about what's the source of the authority of the issuer. Is it a trustworthy organization? Where does their authority come from? When they issue a piece of paper, what are the processes they use for that? So those are all the things we talk about in identity. Paper credentials online are basically done these days by taking a picture of them and scanning them, and that's the where we are today generally with the use of credentials digitally. What we want is a verifiable credential model. Again, I think everyone here should be familiar with this. The issuer provides an issuance of a credential that has got some cryptographic backing to it. They hand it to the holder. The holder, at some later time, the holder puts it in their wallet, holds onto it, their digital wallet holds onto it. Some later time, they present it to the verifier. And there's a verifiable data registry, is a place where cryptographic material goes, such that when the verifier gets the credential from the holder, they are able to verify it, not by contacting the issuer and finding out whether it's accurate, whether it can be verified, but rather by going to some independent place to get information such as public keys and so on to verify the cryptography. We've used this list 1, 2, 3, 4. In fact, verifiable credentials with capital V, capital C, as in defined by the W3C, only talks about the first two, which is who issued the credential and the claims are unchanged. So there is a path to find out who issued the credential via the information in the presentation provided from the holder to the verifier, and there is a signature on it, a cryptographic signature to verify the claims are unchanged. In the non-creds world and places we work, there is a formal way of defining who holds the credential, the binding between the person presenting the credential and the credential itself, how they are associated. That in a non-creds is formally defined as part of the cryptography. In W3C data model standard, that's outside of the spec and has to be determined in some other way. So something like there's a picture of the person in it, and that's the binding, or there's some or there's a DID, and the person proves control over that DID, some sort of mechanism to bind it. And then as well, there's a fourth item, which is available in some types based on the issuer's use case and how the issuer handles it, which is the claims have not been revoked. So those are the proofs that come about. Way less concerned about whether the holder forged it. It's pretty much impossible to forge those types of things. Much more on, do you trust the issuer? And so that's a big piece. There's also concerns about the software that goes along. So do you trust the issuer software? Do you trust the holder's software, and so on? This is different from OpenID Connect and login by Facebook. So I did want to underline that when I talked about this for those new to the topic. Again, I think everyone knows that here. And the big issue is that the issuer is involved in every interaction when you're using OpenID Connect. That there is only a single process, and in that process, the user sort of consents to both the issuer and the relying party, and the issuer delivers the data directly. And of course, in a verifiable credential model, on presentation, the issuer is kept out of the picture, and the interaction is only between the issuer and the relying party. Okay, that's the background on verifiable credentials and what we're using them for. Hyperledger and non-creds is an instance of a way to use verifiable credentials, a verifiable credential type. It's a project at the Hyperledger Foundation. There's a complete open source implementation of it in Rust that is based on the non-cred specification that is also being built and created in the Hyperledger Foundation. This implementation has a long history. Hyperledger Indy came out about 7 years ago in the self-sovereign identity stack. And non-creds has been pulled out and revamped from that Indy implementation. That Indy implementation itself derived from an IBM implementation. So there's a long history of this. The big change that was implemented in pulling non-creds out of Indy is verifiable data registry and agnosticism. Ledger agnostic, which means you do not have to use an Indy ledger to store the objects necessary to have the non-creds interactions. They can be published in a variety of places, and people have already published such objects in a number of places outside of Indy. Indy's still the most common place you'll see them, but it's no longer a requirement, and so that's a big push that we're trying to do in the non-creds community. So what does the non-creds add to the picture, which is privacy, and that privacy comes in privacy preserving elements, and that comes in four flavors. One is selective disclosure, so that when you have a credential that you've been issued and you present it, you don't have to present the entire document. So unlike a paper document where you hand over the paper document to be looked at, you can actually redact, if you will, some of the fields and just present the things necessary for the business transaction you're conducting. And so the verifier can still see who issued it, can still verify that it's the various aspects of it, but they don't see all of the raw data of the attributes within it. Predicate proofs. So predicate proofs are where this is the most obvious zero knowledge proof, where you prove that you are, for example, older than a certain age based on a date of birth in the credential without sharing the date of birth itself. So you're proving something in the credential, but you're not actually sharing the data for it. And by prove, you're not claiming or suggesting self-attesting, you're actually proving it cryptographically. This is a big one of why non-creds is really important, is unlinkable identifiers. So in pretty much every other verifiable credential model and approach, when you share a presentation, you're sharing unique identifiers either for yourself or for the credential itself. So the signet, if you are given a verifiable credential and the way of presenting it is simply to show the other party the credential itself, that the signature on it is a unique identifier. It's very much unique. And so you're actually sharing a unique identifiers for it. And so what an on-creds does is goes very far out of its way to make sure that there is no linkable identifiers simply by presenting a verifiable credential. That is a key place where ZKPs are used, zero knowledge proofs, which we're about to get into. We're getting there, which is that you can prove that the signature, for example, is valid on a verifiable credential without sharing the signature itself. And again, prove being the operative word there. And finally, multi-credential presentation. So inherent in an on-creds is that you can present multiple credentials at the same time and prove that they're tied together, and do that all with selective disclosure. And again, that allows for a data minimization. If you need to prove that you're a lawyer and who you are as a resident of, say, British Columbia, and prove that you're a lawyer, you can present those two credentials, minimize the data shared, and still prove those things, and prove that they were both issued to you or to your wallet. So that's the key features that are added. I should throw in that I do a lot of my work with the digital identity team in the government of British Columbia. This slide sort of highlights why government of British Columbia is so engaged in this. Basically, BC and every other jurisdiction puts a ton of focus on physical identity cards and the importance they provide in underpinning the economy and life in a jurisdiction. The world is moving online. BC, therefore, is investing in figuring out the best ways to provide those same services to make it safe for citizens to operate online, for residents to operate online. And I highlighted duty to protect data privacy and security. And that's in particular why BC is so interested in the on-creds. The organization wants to keep trying to make it that the approach used for verifiable credentials is as private and secure as possible. With that, we move on to the fun part. The high school math edition, zero knowledge proof. So we're going to jump back to your high school math and talk about how cryptographic proofs work with zero knowledge. Thanks to Professor Kazusako, who did the you did early versions of this. The first time I saw this type of thing, Mike Lauder from Sovereign and now in other organizations, but very involved in the on-creds community, did a bunch of these. And actually, it was my daughter that did a lot of the slides and presentation and math parts of these that you're going to see. So kudos to those. So what is a zero knowledge proof? Here's the quote, a method, one party can prove to another party that they know a value X, and we're going to talk about X a lot in this, without conveying any information apart from the fact that they know that value. It's as mentioned, it's the core of an on-creds, and that example that I give, I'm older than 19 based on my date of birth, and but without sharing my date of birth. So one of the approaches used to do, for instance, age verification, and this is proposed in the ISO MDL model and some of the things I've seen in other places is, oh, well, let's just put in, a field that says older than 19, older than 21, older than 25. And so that's another way to get around that particular use case. And it is a super important use case. With an on-creds, you actually put the date of birth in, but the holder does not share the date of birth. They just share a proof that they are older than a given age requested by the verifier. So that's what we're after. This is the interaction that happens. We've got a holder prover that knows some piece of information and wants to prove it without revealing the value. Likewise, the verifier does not know X, wants to verify that the prover knows X without learning about X itself. So both parties have want to participate in this. So let's start with the nursery school edition. So this is an example of, really getting simple with it. So you recall, those who grew up in the age of Where's Waldo, or had kids that did, relished in the knowledge that they knew where Waldo was on any particular page in the book. But they never wanted to let their friends know where they were, because then their friends could claim they found it themselves. So how can you do that? Prove that you know where Waldo is, but not share where Waldo actually is. So the way you can do that is make a sheet of paper that's 4 times the size of the page in the Waldo book, put a little hole in it, and then move the page, the Waldo page around behind it, such that Waldo appears inside that little hole. The person looking at it can see Waldo. They know that you know where Waldo is, but they can't see where on the page the person where Waldo is. So that's the simplest, the nursery school edition. 3 requirements of ZKPs: completeness. If the statement is true, the honest verifier will be convinced that it's in fact it is known by the honest prover. Soundness: if the statement is false, no cheating prover can convince the honest verifier that this is true, except with some small probability, and we're going to get to that in a bit, probability involved in ZKPs. And finally, the zero knowledge component. If the statement is true, the verifier learns nothing other than the fact that the statement is true. They don't actually learn about the date of birth, the value underlying. So keep those in mind: completeness, soundness, and zero knowledge. Attributes. Mentioned this a little earlier. ZKPs are actually probabilistic, not deterministic. You are not going to get 100% knowledge there. You are going to get a probabilistic, but we're getting pretty darn close, and you'll see that. There's an element of randomness always in it, which plays into how the zero knowledge proof is provided. And then we're going to talk about the different forms of ZKPs, notably interactive ZKPs and non-interactive ZKPs. Foreshadowing a bit, non-interactive is better. We'll see why that is. Okay, high school math. Here's where we get to the refresher for high school math. We need to cover functions and inverse functions. So we'll talk about functions. We'll talk about exponents and some of the rules of exponents, because they come into play very clearly in this. The modulo operator and prime numbers. And basically these components that literally you covered probably in what we in North America have as grade 10 math, grade 11 math are all you need to know RSA, the Diffie-Hellman algorithm, SHA-256 hash. All of these cryptographic things are all based on these core components of the math. So a function is an equation for which any x can be plugged in and exactly one y comes out of the equation. One result comes out of the equation. So simple one there, f of x equals x plus 2. So if I put 25 in, f of x is 27. If I put 2 in, it's 4, and so on. So all of these are examples of functions. And basically you have, in these case, one variable that you insert, you do the calculation, and you get your result out. So easy stuff, you know that stuff. The inverse of function is where you reverse it. So given the output, how do you figure out what the input is? And so you do the manipulations. You probably remember doing those. Oh, I can take the 2 over to the other side by converting the plus sign into a minus sign. So we remember that. So x equals y minus 2. And we get the inverse function. So we've got our example of our original function. We can calculate the inverse function. In these ones, in these examples and all of these ones, what you'll figure out is it's pretty easy to go from the original function to the inverse and back. Those are all easy. What we want for ZKPs is a function that is essentially impossible to invert. So what we want is something that we cannot do the inverse for. And that is a core feature, a core requirement. And in fact, what a lot of the work in cryptography is to find, we'll see not just the functions, but the attribute or the numbers, the types of numbers that contribute to making it impossible to invert those. Functions, inverse functions, exponent. So exponent refers to the number of times is a number is multiplied by itself. So 2 times 2 times 2 is 2 to the exponent 3. So again, we remember that x to the 5th. We've got that out. So exponents, pretty easy. You've seen those in regular life. Laws of exponents, non-exhaustive, but we've got a few that are really important here. X to the 0 is 1. X to the 1 is x itself. You just drop the exponent off. X times a gives you x to the a plus b. This is, we're going to use a bunch. Actually, we're going to use all of these, but so again, the example expands out why that is true. So you can see that 2 to the 3rd times 2 to the 2nd is actually 2 to the 5th. So adding the exponents together. And finally, x to the a to the b is x a times b. So again, you can do the same sort of expansion out and see that that's true. So good. We got exponents covered. Whew. This is faster than you did it in high school, I suspect. Modulo operator. This is modulo operator gives the remainder after division. So it's done the same way as division, but the answer, rather than being, you know, how many times does 5 go into 17? Rather, we care about the remainder. And so that's what you see here. 17 mod 5 gives 2. And those of you with a calculator handy or quick with math, 321 mod 17 equals 15. A lot of people like to think of this as the clock ticks. I'm not so good on this one, but I put it up there because many people relate to it. But basically, you count the ticks around, and what you stop at is the modulo 12 of a number. So 27, you go around twice, 2 12s, you come back all the way to the 3. That's the modulo of it. So there you go. That's a way to think of the modulo. Prime numbers, last one, pretty easy. A number divisible only by itself and 1. So infinite number of these. Basically, prime numbers are pretty important in cryptography. And again, that comes back to the need for these things to make that inversion of the function. So we're going to come back to it, but we're going to start again with another example that's commonly used and quite a good one, Alibaba's cave. And we're going to show that how a ZKP is interactive and probabilistic. So that's where these two concepts come into play with this. So Alibaba's cave. Bob's the verifier, Alice is the prover, because of course we can't have anything in this community without Alice and Bob being involved. In the cave, there's 2 paths through the cave, A and B, and there's a magic door between them. So Alice is claiming to Bob that she knows the code to open the magic door. And she's going to prove to Bob that she knows that, but she doesn't want Bob to know that code. She just wants to have it as her own secret. She's not allowed to tell Bob that. So the way Bob and Alice figure out to determine whether she knows it is Bob stands outside the cave, Alice goes in, and then as she goes in, she picks either A or B to go down. So in this case, she picked A. And then Bob does not know which path Alice took. Bob stands there and says, hey, Alice, come out one of the sides. Hey, come out A. And so Alice goes out A. And that was easy because she didn't even have to use her code. She just came out A because she picked the same one Bob picked. So Bob now has some evidence that Alice knows the code, because if she went in B, she would have had to use the code, but you know, she could have gone in A. So Bob really doesn't believe Alice yet. So let's do it again. Alice goes in again, Bob goes in again. This time Bob says, oh, come out B, thinking Alice is going to pick the same way in. Alice can, of course, go in A, since Alice knows the code. She uses the code, goes through the magic door, and comes outside B. And Bob goes, twice. That worked. And now the way you get it is the interactive part. We've got probabilistic. We've got randomness going in. Alice randomly picks A or B. We've got randomness from Bob. Bob's randomly picking A or B to come out. And we've got interaction. We're having it repeated over and over. And every time Alice is coming out the wrong side, the right side. And Bob now thinks, well, there's no way Alice can be reading my mind and know which way I'm going to guess. So I'm getting pretty convinced as I do this, 10, 20, 30 times that probably Alice knows it. So again, this is the probabilistic nature. Bob doesn't know absolutely deterministically for sure Alice knows the code. It's just extremely unlikely that she would have guessed the same thing that he suggested every time. So Alibaba's cave, completeness. If Alice honestly knows the secret code, Bob will eventually be convinced she knows the code. High probabilistic. And that's done through repetition, interaction. If Alice does not know the secret code, it is highly unlikely through repetition that she would be able to convince Bob she knows it. If ever the chance came that she went the wrong one for what Bob convinced, she can't come out the correct side of the cave. She knows it. And of course, zero knowledge, Bob didn't learn the secret code. So now we switch to math. Now we go over to using those 4 elements of high school math, and we figure out Alibaba's cave. So the first thing we do is we need a one-way function. One where the inverse is essentially impossible. So coming back to that, if you know X, it's easy to find f of X. If you know f of X, it's pretty much impossible to go backwards and find X. And this function right here is the one that is used for zero knowledge proofs. So G is some public and known value. G is known by Alice and Bob. X, of course, is the number we're trying to figure out. And then we do modulo P on it, where again, P is public and known value, and it's a prime. So Alice and Bob share G and P. Only Alice knows X. And we're going to use this for Bob to know that Alice knows that Bob can determine that Alice really knows X. So summary of the steps, Bob and Alice agree on G and P. Alice knows X, and so Alice tells Bob f of X. And again, confident that knowing f of X does not allow Bob to determine X. Alice generates a random number, R. So Alice picks one. This is the equivalent to Alice entering the cave and randomly choosing A or B. Alice generates a random number and calculates f of R and shares it with Bob. Bob randomly sends Alice a constant C, which is either 0 or 1 in this first case. And again, this is the equivalent of Alibaba's cave. That's Bob saying, come out A or come out B. Alice defines a new variable, R plus X times C. So Alice knows all of these items. So Alice knows V because she knows all of these things. And then she shares V of F, F of V with Bob. Again, Bob can't determine V. Bob verifies the result by checking that f of R given by Alice, f of X given by Alice to the C, which Bob chose himself, equals the f of v that Alice shared. And if the two sides match, Alice passes. So this is the key slide that says how it's done. And this is the manipulation that goes on with the exponents, basically. F of r times f of x times c equals f of v. That's what we said we needed to check. So let's go down this side. F of r expands to this. F of x to the c expands to this. Then we use our rules of exponentiation. G of x to the c is g to the x times c, and then multiplying that by g to the r is adding to it. So we get r plus x times c mod p, and that's our result on this side. F of v is g to the v mod p, and recall that v was calculated by Alice as r plus x times c, and here we get these matching. The mod p is a factor that just moves out. It's a common factor, therefore we can move it out and have it separated from the rest of the calculations of g. And as a result of that, we get this way that only Alice knows x, only Alice knows r, and yet Bob can be confident that Alice knows is accurately representing those values. So here's some numbers on it. We're going to use really small numbers. X is 4 in this case. Shh, don't tell anyone, only Alice knows that. G we're going to use is 5. This is public. 17 is the prime number. So G is our constant. P is our prime number. F of x therefore is 13. You can do the math on that. R, this random number that Alice picks, is 7. Again, shh, only Alice knows that, not Bob. F of r is 10. Bob then declares either a 0 or a 1 randomly. He chooses it, tells that to Alice, and then V is calculated. Only Alice knows it, again, because V is dependent on X and R, and only she knows it. She does that calculation and then sends, does that calculation, and so she can then do F of V. Here's the actual math for it. We get case 1 of C equals 0, and we get V equals 7, and we get G to the V mod P is 10. Bob verifies that. Bob knows, F of R, F of X to the C. Well, if C is a 0, we know that anything to the 0 is 1. So we wind up this being 10 to the mod 17, which is of course 10. And we get verification that these two, Alice passed. Phew. Case 1. Case 2, here's where we use 1. The only difference here being 13 to the 1th is 13. So this is 10 times 13 mod 17. And if you do the math, you'll find that's 11. Alice passes in either case. Now we have to repeat this process where we use a different R, a different C over and over and over again, interactively. On the first pass, there's a probability of 1/2 of giving the correct value because she knows Bob's going to send either a C0 or a C1. So she can figure out what it is. If they do this 20 times, it's a 1 in a million chance that Alice does not know X. Alice kept guessing the right thing that Bob was going to send a 0 or 1, and so there's a 1 in a million chance that was sent up, that was determined. So that's pretty close to being accurate in only 20 times going through this. Generalizing this, instead of C being 0 or 1, we can choose a C in the range of 0 to P minus 1. Remember, P is our prime number that we're using. So this is the equivalent of adding many paths to Alibaba's cave. Alice has to choose which one of many. Alice or Bob says, come back one of many. And this reduces the number of iterations necessary to prove it. So basically, if you have from Professor Sacco's presentation, she basically explained it as basically each bit in C is an instance of a 0 or 1 iteration. In other words, if we can get C to be 20 bits of information, we've got it down to a 1 in a million chance that Alice guessed correctly and produced the right zero knowledge proof, or the right value to send to Bob. But even if we get it down to 1 back and forth, it's still an interactive process. Alice and Bob are still going back and forth. We want to get down to a simple request response process. Bob makes a request, Alice sends a proof, Bob verifies it. So how do we eliminate that extra step where Bob has to send that extra value C? And that's one more piece of it, which is figuring out how to do non-interactive ZKP. So we've got interactive. We don't want to use repetition to reduce probability. We want to get down to a single back and forth. The way that's done is a hash function H. Again, a hash function, a non-invertible one with a random number I. Alice has used that to define C as f of r, comma I, and using that function that Bob shared. So Bob and Alice both know H, the function, whoops. Bob provides as part of his request I, and Alice makes up R. Alice just creates it because R is a random number that Alice chooses. Bob still knows C. Bob can calculate C once f of r is known, and so it's a shared secret between them, a shared value between them. Bob and Alice both know it, and it is sufficiently random. I is used to prevent replay attacks. So those familiar with cryptography and zero knowledge proofs and verifiable credentials know about replay attacks. But basically, Alice and Bob, Alice requests a proof from Bob requests a proof from Alice. Alice prepares and sends that proof. Along the way, some outsider, Mallory, we often talk about Mallory, malicious Mallory. Mallory listens in and records the proof that Alice sent to Bob. Later, Bob asks Mallory for a proof, and Mallory replays the recorded proof from Alice and claims it to be their own. And Bob can verify the proof, so doesn't know. But by using a different I on every time a request is sent out, the proof that is received is different every time. And as a result, even if Mallory hears Alice's proof, Mallory can't play it back and pretend it's their own because the the random factor, that what's called the nonce, is different. And that prevents a replay attack. So almost at the end. Oops, there we go. In real life, this is what number P looks like in an on-creds situation. P is a little larger than the 17 that we chose in our example. It's quite a large number, and that is a decimal number. C is between 1 and P minus 1. So given P, from the previous slide, C is between 1 and this number. Remember that when we talked about C, C is each bit of C represents a piece of entropy. So we said that 20 bits of it would allow a 1 in a million chance that Alice luckily selected. Well, there's a whole lot more than 20 bits of information in this large decimal number. So a whole lot more likelihood that C is going to give enough that probability is extraordinarily low that Alice could pick it. And then in real life, this is what G looks like. Again, another big huge number. So that completes the coverage of the high school math part. And I'm just at the end of time, so that works of this session, so it works out well. ZKPs, as I mentioned, there's basically 4 commonly used. I go over a couple of them here. Blinding an identifier of the holder. This is the holder binding, that ability that I talked about that is sort of outside of the W3C spec of how that gets done. But in an on-creds, it's very formally defined and it's always the same. Basically, the holder has a linked secret, a big number. A blinded version is put into the verifiable credential. The holder proves to the verifier they know the linked secret, but they don't actually reveal it. And then secondly, they prove that the same linked secret is used with all the presented credentials. Blinding the data values for selective disclosure is the same sort of thing. In this case, the issuer signs encoded versions of the data. And I don't know where I mentioned this, but notice that everything I did, X is a number. X is always a number in zero knowledge proofs. So as a result, if you want to do something with data involved in zero knowledge proofs, you have to encode that data as a number. And so non-creds has a encoding scheme that converts all of the attributes, all of the data elements into numbers. And so it's actually, in a non-creds, it is the encoded value that gets signed, not the actual data. So issuer signs the encoded versions of the data, the numbers representing the data. The holder blinds the signatures in presenting those. The holder proves to the verifier it knows the signature without revealing the signatures. And then the holder reveals the raw data values of the attributes, and the verifier verifies they could they correspond to the signed values. So that's how selective disclosure works, and a little bit on how these signatures are blinded in a non-creds. There's similar capabilities in predicates, similar in revocation, but I just didn't think it was worth going through all the details of those. Pile of references for you. This was based on, I went to this IIW 26 presentation by Professor Sacco, and it was outstanding. This is a little more formal than she did. There's notes on her presentation. She actually got asked to do a second instance of it, so there's notes, but not kind of the presentation and the math. So this is helpful. Mike Lauder did a presentation when he was with the Sovereign Foundation. That's linked here, which is about 160 odd slides that includes detailed math of this. A lot more advanced than the high school math. But if you're interested in seeing all of the steps involved in this, that's a good presentation for that. Here's some other posts about CL signatures, which is the academic paper upon which all of this is involved. Jan and Anna did that. And then some other interesting papers. Oh, David Chom, 1998 paper on blinded signatures, just to show you that this is not brand new stuff. This was the sort of basis upon which Zcash came about, and a bunch of the papers on blinded signatures. So lots of things to look at there. Absolutely, I'll be sharing the presentation. Why do they matter, ZKPs? No shared new identifier to present. For governments, this is huge. Not sharing, creating the SSN or the social insurance number, the social, those identifiers are subject to legislation and so on. Creating new ones is difficult. Also the unlinkability, minimize sharing, and again, unlinkability, fighting back against online tracking. I'm at my time, so I better stop. Some other things in here. But and a call to action, get involved in this. Feel free to reach out to me if you're interested and want to get involved, want to learn more. Welcome to do so. And with that, I'll stop sharing and turn it over because we're at time.
Thank you so much, Stephen. That was a fantastic presentation, super interesting. We covered a lot, so thank you. I think one of the questions is if people can access the slides after.
Yeah.
Great. Sounds good. I can post those as well on the meeting page. So if you go to this page in a moment, I will upload the slides there. So great. Yeah. Thank you so much, Stephen. And thanks everyone for joining in with your working group updates, and we'll see you all in 2 weeks.
Thanks.
Thank you.
Take care.